Okay, let's try to answer some homework questions on this video. So in the lower left, you'll see the agenda. We'll try to get through this, get right into it. So first off, I didn't get any questions from 10.3. The main thing to be careful of in 10.3 that I got a couple of questions, but I answered them by email, was, let's see if this works. Can I draw in here? I can. Okay, so if you've got a shape like a circle that's over here, then you have to be careful about your bounds. If you're finding the area of this circle over here, you don't want to do the integral from 0 to 2 pi, because if you do the integral from 0 to 2 pi, you'll cover the whole circle twice. Really, the bounds you should use here are, well, the circle kind of starts down here at minus pi over 2, and then it goes up and it stops at pi over 2. So if you're trying to do an integral to find the area of this shape, well, this is the bounds that you should use. Yeah, okay, so that's all I'm going to say about 10.3. Then I got a good question here in 11.8. In 11.8, the question was, what happens when I do the ratio test? Sometimes I get like a 0, or sometimes I get an infinity. So, for example, let's see if I can read this. This is, no, I can't read that. Okay, so the question was that something goes wrong in 11.8 number 3. So let's see what we get in 11.8. Wow. Yep, never done this before with this tablet. This is going to take some getting used to. So in 11.8 number 3, the power series we're looking at is the sum of n factorial over n to the n, x to the n. This is a mess. This is like a huge power series. It's got a bunch of stuff going on. And in particular, you can kind of recognize some bad stuff that's going to happen, like the way it happened in the previous section's homework, where there's probably going to be some E stuff going on. So let's see what we do. What we do is just do the ratio test. Nice handwriting. This is going great. Okay, so we're going to find R here. R is a limit as n goes to infinity of a huge absolute value of a crazy fraction. On top, all the n's become n plus 1s. So we've got n plus 1 factorial, we've got x to the n plus 1, and we've got n plus 1 to the n plus 1. And then on the bottom, you just plug in n. So just n factorial over n to the n, x to the n. Okay, we've got some problems with absolute values, namely these x's might be negative. So the absolute values aren't entirely going to go away, they're just going to stay on the x's. In the next step, though, we can flip and multiply. So let's see how this goes. Oh my gosh, just realized the resolution of... Well, we're trying. Let's see how this goes, how readable we can make this. So on the top, we're going to have the n plus 1 factorial. We're going to have the x to the n plus 1. And we're going to have the n to the n from flipping the denominator. And the x has the absolute value still. In the denominator, I've got my n plus 1 to the n plus 1. I've got an n factorial, and I've got an x to the n. But similarly, that x might be negative, so that x has the absolute value bars still. Now we just want to know what cancels. Well, by now we're a little bit used to how factorials cancel. When n plus 1 factorial cancels with n factorial, all that's left is an n plus 1. And then we cancel one of these n plus 1s with one of these n plus 1s. And then what's going on with the x's? Well, most of the x's cancel. There's one more x on top than there is on the bottom. So in total, what we've got at the end here's the limit as n goes to infinity of, I've got an absolute value of x, and I've got this lovely n over n plus 1 to the n. Now the absolute value of x we can just take out of the limit because it doesn't have any n's in it, so that's good. And then what's going to be left is this limit, which is maybe familiar at this point, and it comes out to 1 over e. So the whole limit at the end is absolute value of x over e. Okay, now what do we want to do with the absolute value of x over e? Well, the point is that that's the ratio, and the series definitely converges by the ratio test whenever the ratio is less than 1. So we set that less than 1, and see what interval we get. So I'm going to go up to the top here. How far over can I go? Not very far. Okay, so I'm going to take this r that I got, it was the absolute value of x over e, and set it less than 1. When I do that, I just get an absolute value inequality. Absolute value of x is less than e. How do you make the absolute value of a number less than e? Well, you have to make sure it's not too negative, and you have to make sure it's not too positive. It can't be too big in either direction. And I'm pretty sure the directions here say don't check the endpoints. Yeah, they don't check the endpoints, so we're going with this for the interval. This is the interval of x's where this series converges. Yeah. One more thing, there's a question about the radius. Remember that the radius of convergence is just the radius of this interval. And if anybody ever asks you the radius of anything, you say, okay, where's the middle of the thing? The middle of this thing is 0. The middle of this interval is 0. And then how far is it from the middle to the edge? And it's e from the middle of this interval to the edge. So the radius is e. And that should do it. Normally, in like a more reasonable series, you would be able to plug these endpoints in and check them, because the ratio test is actually inconclusive on those endpoints. So in this problem, I don't know. I mean, we were able to do the interval. We just can't really get the endpoints very well because plugging in e causes some weird stuff to happen. So, okay, so that's number 3. In these problems, you should try, when you're in the power series problems, you should try not to do the whole limit with all the ln's and stuff. You should try to refer back to a limit you recognize from before, like this one. So this one comes out to 1 over e, and you should try not to do it repeatedly over and over. And then the other thing to remember is that the absolute value of x escapes the limit entirely and doesn't interact with it at all. So this absolute value of x is just going to be in the answer, and then you can do the limit without the absolute value of x. Cool. Okay, so that's number 3. Let's see if I can clear this. Yeah. The other question I got from these 11.8s was, what if I get a radius of 0 or a radius of infinity? Or an r of 0 or an r of infinity? So, like, what's the deal with that? So, say you have a series, and you do the ratio test. This handwriting's great. Okay, so say you have a series, you do the ratio test, and you get that r is this limit, and it's something crazy, right? And you do a bunch of work. And normally you would expect that there would be an x in the end of it, but sometimes you don't get an x. Sometimes you get a 0, or like a number. If you get that number, you do the same thing you do otherwise, which is you check, is it less than 1? And if it's less than 1, then yes, it converges. And that's weird because it means it converges regardless of x. So in this situation, you would say, it converges for all x. If instead you get to the end, it's pretty, okay, sure, great. If instead you get to the end and you get like infinity, you still do the same thing. So no matter what you do when you do the ratio test, you find r, you get to the end, and then you check to see if the thing is less than 1. If there's x's in this equation, you just solve for x, you'll get an interval. If there's a number, then this comes out either true, which means every x works, or in this case, false, which means no x's work. so the radius of convergence is 0. Wow. So the radius of convergence here is 0. That means like the interval of things that work is so small over here, so small that that like nothing works. There's nothing works at all. Okay, so that's what happens if you have a radius, like an r equals 0, you get a huge radius because you get a huge interval, or r equals infinity, you get a tiny radius, which is a tiny interval. Yeah, so, cool. Constant 0, yeah. My r is x over e, but the book says that it's e. Yeah, so in that problem where you get r equals x over e, it created an interval whose radius was e. So it's the difference between the r and the radius. Okay. That is that. Okay. Last question is in 11.9. On 11.9, when you do the problems, you're probably going to get an answer that's off a little bit from the answer in the back. So we're going to look at what was asked about. I got the question was about 11.9 number 2. In 11.9 number 2, the question is to find a series for 1 over 1 minus x squared. What I told you in class was that you should use the fact that 1 over 1 minus x has a nice series. It's just the sum of x to the n, starting at 0. So we have a series to start with. And then if we can figure out how to turn our starting series into a new series, then that'll be how we'll get the answer. So the question is like, okay, great. I've got this function. It's not my favorite function. And I want to know how to get from this function to this new function. Like, how do I get there? And the answer is, well, this new function happens to be the derivative of the previous function. So I'm going to write that down as a sentence. I'm going to say, the new function is the derivative of the old function. The reason it's useful to just directly translate like this is that then I have an equation I can work with. Yeah, okay, so I've got the new function is the derivative of the old function. And then I have like a name for the old function, so I can just replace the old function. So I get I still have the derivative of, but that old function can be written as this series. There's a little issue that, this series, it only works for certain x's, but we're just going to go with it for now. So the new function is the derivative of the old function, and then the point of 11.9 is that you can do calculus inside the sum. So you can just do the power series. You can just do the power rule inside the sum, as long as you knock out the first term. Because that constant term, n equals 0 is the constant term, that gets destroyed by the derivative. So, yeah. I just realized that my lighting situation is so bad that my eyes are made of these, like, square... Oh my gosh. Okay, well, anyway, back to the math. So we're doing the derivative of the power series, we're going to do the derivative under the sum, we just do the power rule, n x to the n minus 1. So this is going to be my final answer. I'm just going to circle this. And then we're going to look in the back and probably see something different. The question is our answer actually the same thing as the answer in the back? And if so, then I don't really care what the back says. I'm just going to go with our answer. So here's the answer in the back. Oh dear. Help. Oh dear, I've got cursive. Okay, the answer in the back. The answer in the back is the sum from n equals 0 to infinity of n plus 1 x to the n. Okay, so we've got our answer and the answer in the back. I want to know if my answer is right. It doesn't have to look exactly the same. I just have to make sure it's equal, that it's the same. And the way that you can tell if two series are equal is just start writing the first few terms. So for example, the first term of this series starts at n equals 1. So we'll plug in n equals 1. And I'll get 1x to the 0. That's 1. The next term would be n equals 2. So I'll plug in 2. I get 2x to the 1. The next term is n equals 3. I get 3x to the 2. Now we can kind of see the pattern. Next one is 4x to the 3, and so on. So this is our answer. Our answer encodes the information 1 plus 2x plus 3x squared plus 4x cubed, and so on. Then we can go look at the answer in the back. Say, like, what's the answer in the back doing? Well, the answer in the back starts at n equals 0. So you plug in 0 for n. You get 1x to the 0. Yep, that's right there. Then you plug in n equals 1. You get 2x to the 1. Yep. Next up is n equals 2. You get 3x to the 2. It's all great. It's all great. So these are exactly the same. And so both of these answers are perfectly fine because they're equal. They're the same thing. So that's my answer, basically, is if you're taking the derivative of a series and your answer doesn't match the back, kind of don't worry about it. Just make sure that your answer is actually the same as the answer in the back. And if so, then you're good. Yeah, I think that should help. If you want to make your answer look like the answer in the back, all you do is you can kind of see what happened here. If you want to take your answer and shift it down, let's see if I can set this up. So you aren't required to do this, by the way, but if you want to turn your answer into the answer in the back, you start with your answer. You say, oh, it starts at n equals 1, that's terrible. So instead, I'm going to start at n equals 0. Because I know the answers in the back are obsessed with starting at n equals 0. Then, since I've shifted this n down by 1, all of my n's that show up, like if I just write this again, if I just write my nx to the n minus 1, then this is wrong, because my n's here in the new version, in the red version of the answer, are all 1 too small. Because I moved n down from 1 to 0. So these n's are too small now. So to compensate, all we have to do is take all of our n's and make them 1 bigger. So just take this n and make it 1 bigger. And take this n and make it 1 bigger. So if you shift the index down by 1, if you shift the 1 down to 0, then all your n's are 1 too small, and that means you have to make them 1 bigger. So then we'll get this. And then if you simplify this, you'll get the answer in the back, because this plus 1 and minus 1 will cancel. And so you get n plus 1 x to the n starting at n equals 0. So these answers are all the same, but for the purposes of a quiz or something, you should just take the derivative and feel powerful that you're able to take derivatives of crazy functions by just doing the power rule. And that's the point. And don't worry about shifting them down, except to check your answer in the back. Okay, that's all the questions I got that were easiest answered in this video. I hope it was useful. I'll see you Wednesday. There's going to be a quiz. Quiz is going to be on those sections. First thing in the morning. First thing in the morning Wednesday, I'll bring you that quiz. So I'll see you then. Thanks.